Sometime in the early weeks of July 2026, a cluster of seismic monitoring stations fixed to the flanks of Mount Rainier, the 14,411-foot ice-capped volcano that rises above the greater Seattle skyline on clear days and serves as the unofficial landmark of the Pacific Northwest, began registering a pattern of low-frequency earthquakes that volcanologists at the United States Geological Survey had not seen concentrated in that particular section of the mountain's upper edifice in the entire span of their modern monitoring record. Not a single large quake, not the kind of shaking that rattles windows in Tacoma or sends alerts to every phone in Puyallup. What the sensors picked up was quieter than that, and in some ways more instructive, a signal that tells scientists something is moving beneath the mountain that was not moving in the same way before. And the question of what is moving and where it is going is the one that the USGS Cascade Volcano Observatory is now working to answer. This is what the monitoring data actually shows. What scientists at the Pacific Northwest Seismic Network, the USGS Cascade Volcano Observatory in Vancouver, Washington, and NASA's Jet Propulsion Laboratory, whose satellite-based radar systems provide independent ground deformation readings, have confirmed in their most recent published reporting. No eruption has been forecast. No evacuation has been ordered. But what the instruments are detecting is real, it is scientifically significant, and it involves a mountain that the United States Geological Survey has formally identified as one of the most dangerous volcanoes on the planet, not because of how likely it is to erupt in any given year, but because of what happens to millions of people when it does. The technical term for what the instruments have been logging is a low-frequency earthquake swarm. The distinction between low-frequency and high-frequency earthquakes matters more than the terminology suggests, because the two types of seismic signal point to fundamentally different physical processes happening underground. A high-frequency earthquake is the kind most people are familiar with, the sharp, brittle fracture of cold rock snapping under stress. You can feel those. The seismic waveform they produce has a sharp, distinctive character on a seismograph, a clear onset and a rapid decay. Low-frequency earthquakes look different. Their signal is smoother and slower, and their origin is not in cold rock fracturing, but in the movement of fluids, magma, hydrothermal water, volcanic gas, forcing their way through cracks and conduits deep in the rock. When you see a swarm of low-frequency earthquakes on a volcano, the signal is not telling you that the mountain is falling apart. It is telling you that something fluid, and fluid in origin, is in motion underground. The swarm detected beneath Mount Rainier's upper edifice this month was shallow, located at depths between roughly 2 and 6 kilometers beneath the summit, and it occurred in a zone that does not correspond to the typical locations of background seismicity that scientists have been tracking at Rainier for decades. That geographic mismatch is what elevated it from routine to something that warranted an updated monitoring advisory from the Cascade Volcano Observatory. Simultaneously, GPS ground deformation stations planted across Rainier's flanks, part of a monitoring network that has been measuring the mountain's shape to sub-centimeter precision for years, recorded a subtle but measurable pattern of ground uplift localized to the upper south flank of the volcano. The uplift is small, millimeters, not meters, but ground deformation on a volcano is not a random or meaningless event. When the surface of a volcano lifts, even slightly, the most straightforward physical explanation is that something beneath it is expanding, either magma moving upward into the shallower crust, or hydrothermal fluids under elevated pressure, or a combination of both interacting with the rock above them. The combination of those two signals, the low-frequency earthquake swarm and the ground uplift detected in the same time window, is what the monitoring community is taking seriously, because the two signals together tell a more coherent story than either one in isolation. To understand why those two signals together are being treated with scientific care, rather than dismissed as background noise, you have to understand something about Mount Rainier that is not widely appreciated outside of volcanology and disaster planning. Rainier is the most heavily glaciated peak in the contiguous United States. 26 named glaciers sit on its flanks, holding roughly 1 cubic mile of ice and compacted snow accumulated over centuries. It is that ice, not lava, not pyroclastic flow, not the dramatic explosive imagery that people tend to associate with volcanoes, that makes Rainier uniquely dangerous among all the volcanoes in the Cascades. A significant eruption at Rainier, or in some scenarios not even a full eruption, but simply a large-scale hydrothermal explosion or volcanic debris avalanche, triggered by rock that heat and hydrothermal alteration have weakened over decades, would interact with that ice in a specific and catastrophic way. The energy and heat would melt the glaciers. And melted glacier water, mixed with volcanic rock, ash, and debris in motion down a steep slope, does not flow gently downhill like a river. It moves as a lahar, a volcanic mud flow that behaves more like fast-moving concrete than water, capable of traveling dozens of miles from its source at speeds of 20 to 40 miles per hour, while carrying boulders and destroying everything in its path. The valleys that drain Mount Rainier's flanks toward Puget Sound are not empty corridors of wilderness. They are the valleys where roughly 150,000 people live. The communities of Ording, Sumner, Auburn, Puyallup, Pacific, and Buckley sit on the floors of those valleys, in many cases surrounded by walls of terrain that would channel a lahar directly through the center of town before any diversion was possible. Pierce County Emergency Management has modeled what a lahar from a major Rainier event would look like in the Puyallup River drainage, and the findings have shaped the county's disaster planning for more than 2 decades. A lahar traveling down that valley under realistic eruptive conditions could reach the city of Ording, a community of roughly 9,000 people, in as little as 30 to 40 minutes from the moment a significant eruption begins. 30 to 40 minutes is not a generous window for a population that includes schools, nursing homes, a correctional facility, and a system of roads that narrows to a small number of exits at the valley floor. It is enough time for a person who is already moving, in a vehicle that starts immediately, on a road that has not yet become congested, to reach high ground. It may not be enough time for everyone. It is definitely not enough time for the people who have never thought about which direction high ground is. The lahar threat dominates the conversation around Rainier for good reason, but it does not exhaust the consequences that a significant eruption would produce for the broader Pacific Northwest. Volcanic ash from a major event at Rainier, carried by prevailing winds at the time of the eruption, could be deposited across a wide area of western Washington, and depending on upper atmosphere wind direction, could reach eastern Washington, Oregon, and Idaho. Volcanic ash is not simply a cosmetic inconvenience. At millimeter-scale accumulations, it renders roads nearly undrivable, clogs engine intakes, and forces the grounding of commercial air traffic. Seattle-Tacoma International Airport sits approximately 60 miles northwest of the volcano. Portland International Airport is farther, but remains within reach of significant ashfall under the wrong wind conditions. The electrical transmission infrastructure across the Pacific Northwest, open-air lines and substations that ash accumulation can short-circuit, is a documented vulnerability that utility companies have assessed and for which contingency plans exist but have never been fully tested at scale. Municipal water systems across the affected region draw from surface sources that ash contamination renders unusable without treatment infrastructure that was not designed to process volcanic material. And the Interstate 5 corridor, the main north-south artery connecting California, Oregon, and Washington, runs through multiple lahar inundation zones in the valleys south and west of Rainier, meaning that in a significant event, the primary road network for the entire region would likely be compromised by mudflow damage well before secondary hazards became the dominant concern. Here is the part of this story that the USGS wants the public to hold clearly. What the instruments recorded this month does not constitute a prediction that Mount Rainier is about to erupt. The volcanic alert level for the mountain currently remains at normal, the lowest of the 4 levels the USGS uses to communicate volcanic hazard status to the public, indicating that the volcano is exhibiting behavior that falls within the range of what scientists consider background activity, even as that background has recently shifted in ways worth watching. Volcanoes can show elevated seismic activity and ground deformation for months or years without ever producing an eruption, because the magmatic and hydrothermal systems that generate those signals are dynamic, complex, and do not resolve along a single simple trajectory toward either eruption or quiet. The Cascade Volcano Observatory team has increased the frequency of its data review and is monitoring the situation with closer instrumental attention than the standard baseline requires. That decision is not a sign that an eruption is considered likely. It is a sign that the pattern of signals warrants more watching than normal, and in volcanic monitoring, that distinction is precisely the one that matters. To calibrate what this kind of escalation in monitoring attention means in practice, It helps to look at the full historical record at volcanoes in the same Cascade Range, a record that spans both the encouraging and the sobering. The most instructive example sits roughly 100 miles south of Rainier, on a clear axis through the same volcanic arc. Mount St. Helens, the most active volcano in the contiguous United States, provided the Pacific Northwest and the world with what remains the defining modern case study in volcanic monitoring, escalating unrest, and the cost of underestimating a signal once it has been seen. Beginning in March of 1980, St. Helens began showing precisely the kind of indicators that Cascade Volcano Observatory scientists now watch for across all monitored Cascade volcanoes. Shallow earthquake swarms, ground deformation visible and measurable as a growing bulge on the north flank, and increasing steam and gas emissions from the summit area. Scientists from the USGS and the University of Washington tracked those signals in real time. Exclusion zones were established. The public debate about how seriously to take the warnings and how large the restricted area should be was contentious, unresolved, and still ongoing on the morning of May 18, 1980, when the north flank of St. Helens failed in the largest landslide ever recorded in human history, triggering a lateral blast that killed 57 people and leveled over 230 square miles of forest in roughly 10 minutes. A USGS volcanologist named David Johnston, monitoring the event from an observation post that was believed to be safely outside the potential hazard zone, died in that blast. His last transmission, "Vancouver, Vancouver, this is it," is still one of the most vivid records of how quickly a volcano moves from watched to erupted. The other historical reference relevant to Rainier sits not in the 1980s, but in deep prehistory, and it is the one that emergency managers in Pierce County return to most often when explaining what they are actually planning for. Approximately 5,600 years ago, a massive sector collapse of Mount Rainier's summit produced the geological feature that researchers call the Osceola mudflow, a lahar so large that it traveled the entire distance from the summit of the volcano to Puget Sound, burying what is now the Kent Valley under as much as 70 feet of volcanic debris and rock. The Kent Valley today is a densely developed corridor of warehouses, distribution centers, manufacturing facilities, and residential neighborhoods that function as essential logistics and commercial infrastructure for the entire greater Seattle region. The flat valley floor that those businesses and communities occupy was built by the last time Mount Rainier produced an event of that scale. The mountain has done this before. The geography remembers it, even when the population living on top of that geology does not. Let's go a little deeper into what the instruments are actually detecting inside the mountain right now, because the internal mechanics of how a volcano like Rainier generates the signals the monitoring network picked up this month are genuinely worth understanding, and the picture they paint of what is happening beneath the surface changes the meaning of the July data considerably. Mount Rainier is not simply a pile of volcanic rock that happens to be shaped into a mountain. It is an active geological system driven by heat from below, heat from a magmatic source that has been intermittently supplying energy to the overlying crust for hundreds of thousands of years. At depth beneath the edifice, magma exists. The questions that volcanologists work to answer are not whether magma is there, it demonstrably is, because otherwise the volcano itself would not exist, but where it currently sits in the plumbing system, whether it is in motion relative to its position last month or last year, and whether any motion is oriented toward the surface or redistributing within the deep system. The shallow earthquake swarm detected in July falls in a zone that geologists associate with the boundary between the competent rock of the upper volcanic edifice and the active hydrothermal system that circulates superheated water through the mountain's interior. Mount Rainier has one of the most extensive hydrothermal systems of any volcano in the Cascade Range, expressed visibly at the summit as steaming fumarolic vents where volcanic gases and hot water escape through cracks in the crater walls, and measurable in the chemistry of springs and streams that drain the mountain's flanks at lower elevations. Hydrothermal systems are thermally sensitive to changes in the magmatic heat source below them. When magma moves upward into the shallower crust, even by a modest amount, it increases the heat delivered to the overlying hydrothermal system, raises the pressure of fluids circulating through the rock, and can produce exactly the kind of shallow, low-frequency seismicity that the July swarm represents. The GPS ground uplift detected simultaneously is consistent with that same mechanism. Fluids under elevated pressure in the upper portion of the hydrothermal system physically pushing outward against the surrounding rock and causing the surface to rise by small but measurable amounts. What the scientists cannot yet determine from the available data is whether the heat source driving this change is a pulse of magma moving into the shallower crust from deeper in the system, or whether it reflects a reorganization of the existing hydrothermal circulation that does not involve any new magma movement at all. Both explanations are physically consistent with the current signals. Both are being tested against incoming data, and the difference between them matters, because one resolves on its own as fluids redistribute, and the other represents the early signature of a process that may not. There is a detail about the monitoring work at Rainier that rarely appears in news coverage, but that gives the July activity an unexpectedly concrete dimension. The closest continuous gas emission monitoring station to Rainier's active fumarolic zones is maintained by USGS technicians, who must physically reach it during summer months by crossing active glacier ice above 13,000 feet of elevation to service instruments that would otherwise be inaccessible. The gas measurements that scientists are using right now to assess whether volcanic sulfur dioxide emissions from the summit area have changed, one of the key chemical indicators that distinguishes magmatic unrest from purely hydrothermal activity, come partly from instruments that a person had to climb a glacier to check. The data the scientific community is relying on to understand what is happening inside the mountain requires people willing to work on a potentially restless volcano to collect it. The scientific community's confidence in its ability to monitor and interpret volcanic unrest has been built on experience at volcanoes around the world, and the full spectrum of outcomes in that record ranges from extraordinary success to preventable tragedy. The 1991 eruption of Mount Pinatubo in the Philippines stands as the most instructive example of what effective monitoring and decisive action can achieve. Scientists from the USGS Volcano Disaster Assistance Program and the Philippine Institute of Volcanology and Seismology tracked Pinatubo's escalating unrest for 2 months before the eruption, identified signals that indicated an unusually large event was building, and coordinated the evacuation of an estimated 58,000 people from the surrounding area before the second largest volcanic eruption of the 20th century occurred. The eruption's pyroclastic flows would have killed tens of thousands of the people who were no longer there. It is one of the clearest documented cases in which monitoring data, scientific interpretation, and government willingness to act on that interpretation directly produced a mass casualty outcome that was far better than the counterfactual. The Pinatubo outcome was not automatic. It required monitoring infrastructure, a scientific team trusted enough to be heard, and decision-makers willing to order an evacuation before the eruption confirmed the warnings. The question of whether all of those conditions currently exist in Pierce and King Counties, Washington, is one worth asking now. The specific vulnerability of communities in Mount Rainier's lahar zones is something that emergency managers have been addressing with increasing urgency and with results that are genuinely mixed in their completeness. Pierce County has installed a network of lahar detection sensors in the river valleys draining Rainier's south and west flanks, instruments designed to detect the seismic signature of a lahar already in motion and trigger automated warning sirens in the valley communities below. Orting has those sirens. The county has conducted community evacuation drills. The drills have produced both encouraging and difficult findings. Most residents who participated from home were able to reach high ground within the modeled window, but a significant portion of Orting's daytime population is distributed across schools, workplaces, and agricultural operations in ways that require different logistics than a residential evening evacuation. Getting the children out of Orting Elementary School, a building sitting in the direct path of a Puyallup River lahar, requires buses, drivers, clear roads, and an immediate decision from the moment the first warning sounds. Achievable. Contingent on every link in that chain functioning correctly on the day the signal is real and not a test. There is a connection between what is happening at Mount Rainier right now and the broader set of geological hazards in the Pacific Northwest that rarely appears in coverage of either system in isolation, but that geoscientists have been documenting for years. The Cascade Volcanic Arc, the chain of volcanoes to which Rainier belongs, exists because the Cascadia subduction zone exists. The Juan de Fuca plate sliding beneath the North American plate generates the magma that feeds every Cascade volcano. The same plate boundary mechanics that produce the threat of a Cascadia megathrust earthquake also drive the subduction that sustains Mount Rainier's magmatic system. The two hazards are not separate problems sitting in separate columns on a risk register. They are expressions of the same geological process operating at different depths and on different timescales. Historical records and geophysical modeling have shown that large subduction zone earthquakes can alter the stress state in the overlying volcanic arc in ways that affect volcanic systems, not deterministically and not in simple linear cause and effect chains, but with a documented probability that scientists who monitor both systems take seriously. The USGS Cascade Volcano Observatory explicitly includes post-Cascadia event volcanic surveillance protocols in its operating procedures. For the Pacific Northwest, the risk picture is not an earthquake risk plus a volcanic risk. It is a geological system risk in which the components interact. What is actually being done in real time to monitor the current change at Rainier reflects the capabilities of what is genuinely among the world's most sophisticated volcano surveillance systems. The Cascade Volcano Observatory operates seismometers, GPS deformation stations, gas spectrometers, and high-definition webcams across Rainier's flanks in coordination with the Pacific Northwest Seismic Network's broader regional array. Satellite-based INSAR radar, operated by NASA's Jet Propulsion Laboratory and accessed by the USGS through scientific collaboration agreements, provides ground deformation measurements that don't require physical instruments to be present on the mountain in winter when access is impossible. The combination of ground-based and satellite monitoring gives scientists a picture of what is happening inside Rainier that is continuously updated, redundant across multiple independent measurement technologies, and far richer than the instrumentation that existed when St. Helens began its pre-eruption unrest in 1980. What the monitoring cannot do is determine exactly what the system will do next. What it can do is tell scientists the current state of the system, how it is changing day to day, and how those changes compare to the behavior patterns seen before eruptions at other monitored volcanoes globally. That is what it is doing right now. That work is ongoing. For the residents of the Puyallup, Carbon, and White River valleys, for the families in Orting who send their children to school on a valley floor that the geologic record says a lahar has reached before, and for the millions of people living in the greater Seattle and Tacoma metropolitan area within range of Rainier's broader effects, the July monitoring updates carry a weight that goes beyond the technical language of volcanic alert levels and deformation millimeters. It is the concrete, practical weight of people who need to know whether they are in an evacuation zone, whether they know their route to high ground by heart rather than by memory of a map they saw once, and whether the emergency kit they may or may not have in their home contains enough to matter in a scenario where supply chains across the entire region are disrupted for weeks. Pierce County Emergency Management publishes lahar inundation zone maps and evacuation guidance built specifically around Rainier hazard scenarios. The gap between the existence of that information and its presence in the actual household decision-making of the people who live inside those zones is one of the most consequential measurements this month's data produced. Volcanoes cannot be scheduled. No instrument array, no satellite system, no geophysical model translates the July signals at Rainier into a date on a calendar or a probability high enough to call an evacuation. That uncertainty is not a gap in the science. It is the honest operating condition of every volcanic monitoring program in the world. And it is the condition under which all preparation has to happen, before the event rather than in response to it. The Cascade Volcano Observatory will continue publishing updates as the data warrants, and the Pacific Northwest Seismic Network will continue logging every signal that moves through the mountain. Keep watching those monitoring updates. Keep watching the progress, or lack of it, on lahar early warning coverage, valley evacuation infrastructure, and school and workplace preparedness programs in the communities at highest risk. And if you live anywhere in the shadow of Mount Rainier, in a valley whose floor was built by what the mountain has already done, the July data is a reminder that the mountain has its own timeline and has never asked anyone's permission to follow it. The scientists watching it are doing everything the current state of the science allows. Whether the people living beneath it are ready is still a question that the mountain itself will eventually answer.